Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor at the Department of Computer Science in Jesus and Mary College, University of Delhi. So friends, we have been talking about operating systems in the past few lectures of this series, and if you recall, in the last lectures of this series we were talking about a very important topic, a very important function of the operating systems, that is memory management. So in continuation with that discussion, today also we are going to talk about memory management. In today's lecture we are going to talk about how memory is allocated by the operating system to the various processes. Then we will be talking about what are the problems which occur when memory is allocated to different processes. So what is the different types of issues which can come, what is the phenomena of fragmentation. We will talk about internal fragmentation and external fragmentation also. Besides this, in the memory management unit we will be talking about segmentation, and we will be talking about paging also. So this is a very comprehensive module of memory management in operating systems, and this lecture will be very useful for students who are pursuing BSc Honours Computer Science or Computer Science BSc General, or even the MCA students. So friends, we will start with our discussion. So we had in the last lecture, just to build a perspective, very quickly we will just revisit what we had done in memory. So we had discussed that the computer's memory, where we are talking about the memory as the memory which is directly accessible by the CPU. So whether it is the RAM or it is the cache memory, so this memory is directly accessible by the CPU, and any process which is to be executed by the CPU has to remain in the memory. So therefore there is a continuous swapping in and swapping out of processes which keeps on occurring in the computer's memory, because the CPU is constantly taking data from there. And from where is the data coming? Of course the data is coming from the secondary storage into the memory. Then when we are talking about this swapping in, swapping out, then there is also this various kinds of schedulings or various kinds of algorithms which are discussed, as in which process will remain in the memory and which process will be moved out of the memory. So we had discussed about all these factors in the last lecture. Now today we are going to first discuss how memory is actually allocated to the different processes, right? How memory allocation takes place. So the simplest method in any computer for allocating memory is to divide the memory into several fixed size partitions, and each partition will contain exactly one process. Now the degree of multiprogramming as in how many programs can be executed concurrently on a system, it is obviously bound by the number of partitions. Why? Because we are saying that for every partition there will be for every process there will be one partition of the memory. So therefore we say that there is a multi-partition method, and in this, whenever a partition is free, whenever that compartment of the memory is free, then a process will be selected from the input queue and it will be loaded into the free partition, and when the process terminates, then obviously the partition which was allocated to this process, it will become available for another process. So although now this method of partitioning is no longer used, this is just to understand how the allocation takes place. Now in the present time operating systems, the partitioning scheme which is used is actually called the variable partitioning scheme. So this is not fixed, but it is variable partitioning scheme. Now in this, what happens, that the operating system will keep a table, and that table will indicate that which parts of the memory are available and which parts are not available or which have already been occupied. So initially what happens, when no processes are running, the complete memory is available, and there is no it is available for user process, and therefore this entire one large block of available memory, and this is known as a whole. Now memory contains a set of holes of various sizes, right? So small and big different sizes can be there. Now what happens? Now first process enters the system, right? So when a process enters the system, it is put in the input queue. We've already discussed this, that how process execution will take place. So the process is placed in the input queue as it enters the system. Now the operating system will take into account the memory requirement of all the processes which are there in the input queue, right? So process P1 requires how much memory, process P2 requires how much memory. Is the task of the operating system to keep a track of this. Now the amount of available memory space which is determined when the processes are allocated memory. Now the operating system is actually going to allocate the memory to the process depending upon the available memory and what is the requirement of the process. So when a process is allocated the space, then it is loaded into the memory, and then it will compete for CPU time. We've already discussed this, that any process which is to go for the CPU has to be loaded into the memory. So after it gets placed in the memory, then it will compete for the CPU, and when the process terminates or it is it is sort of interrupted, then it will release the memory which the operating system will then fill with another process from the input queue. So this is a very, very systematic process, in which the whole thing is working. Memory is given to a process, the process executes in the CPU. When the process completes or is interrupted, the memory is released and it is given to another process from the input queue. So at any given point of time, we will have a list of available block sizes and an input queue. So there are two things. One is the input queue, which is having the details of all the processes which are wanting to enter the memory, and we have the list of the block sizes, which is the available memory blocks in the system. Now operating system is all powerful, and it can order the input queue according to a scheduling algorithm, and then memory is allocated to the processes until when the memory requirements of the next process cannot be satisfied. When will this be? Because there is no available block, there is no available hole which is large enough to hold that process. So till the time there is place in the memory, the operating system will go on assigning the processes to the memory. Now the operating system will wait. Now when there is no not enough memory left for a process to execute, then there is nothing to be done. The operating system has to wait until a large enough block is available, or it can skip down the input queue to see whether the smaller memory requirements of some other process can be met, because the operating system cannot take away the resource like this, because there is again the scheduling and the process management methods are there. So it will wait till the time memory is available, or because smaller chunks are available, so it will look in the input queue that if there is a process whose requirements can be fulfilled with this available memory, then it will skip the queue and it will bring that process and assign the memory to it. Right. So in general, the memory blocks which are available, they comprise a set of holes of various sizes, and these holes are nothing but the available blocks of memory. They are scattered throughout the memory. So whenever a process will arrive and it will need memory, the system will search the set for a hole, and which is what is the size of the hole is important, because the hole has to be large enough for the process to be accommodated in it, right? So if the hole is not large, then it is it cannot be allocated, right? And if the hole is very large, then what will happen? The hole will be split into two part. So first part will be given to the arriving process, and the next part or the other remaining part will be returned to the set of holes. So like this, you know, the operating system constantly keeps on assigning processes, assigning memory to the waiting processes. Now whenever the process will terminate, then the block will be returned, and then it is again, whenever a block of memory is freed, then it is placed back in the set of holes. So if the new hole is adjacent to the other holes, then these are merged to form one larger hole. But this is not necessary, because we are saying that the holes may be scattered throughout the memory. Right? Now, very important point which needs, you know, the system which will have to check is that there are processes, are there any processes which are waiting for memory, or whether the newly freed and recombined memory can now satisfy the demands of the new waiting processes, right. So this procedure is very important, and this is, you know, because this is working in a very, very dynamic fashion. It's actually called the dynamic storage allocation problem, right. So this has to satisfy that if, you know, we have a request of size n, right, from a list of free holes, right. So then there are three ways, you know, it can be done. So actually for memory allocation, there are three different strategies, there are three different allocations strategies or three different allocation algorithms which are used whenever, you know, a new process is to be assigned a memory. So the three algorithms are the first fit algorithm, the best fit algorithm, and a worst fit algorithm. These are called strategies, or they can be called as algorithm, right. So the worst fit strategy is the very common strategy, right. But first let us look at the first fit. So the name itself suggests that whichever is the first hole that is big enough to, you know, be allocated the process, that hole will be assigned to the process. So now this searching of the first fit, you know, the hole can start from either ends of the memory. It can start from the beginning of the set of holes, or it can start from the location where the previous first fit search ended. This can be worked out, right. But as soon as a hole large enough to, you know, accommodate the process is found, the search is stopped, right, and that hole is assigned to it without, you know, without worrying about whether a better match could have been found. Whichever is the first fitting hole, which can satisfy the memory requirement of the process, that will be assigned. The second strategy is actually a best fit strategy. Now here best fit means that the smallest hole will be allocated that is big enough to hold the process, right. So the entire list will be searched, and in that list whichever hole will produce or whichever hole will give the smallest, you know, place, but it will also be big enough to hold. So in a way we are trying to minimize wastage here, right. So sometimes we see that the list of holes is ordered by size. In that case, you know, the system doesn't have to search through the entire list, because it will know the size is, it is ordered by size, so it will know that which is the best fitting hole for this particular process. But if it is not a sorted list, then of course it will have to search through the entire list. So this strategy will produce the smallest leftover hole. Why? Because it is minimizing the wastage. The third strategy is the reverse of the best fit strategy, or the opposite of the best fit strategy, and it is known as the worst fit. Worst fit means that we will allocate the largest hole which is available, right. So again the same thing applies, that the entire list will be searched unless it is sorted, and it will then allocate the biggest hole to the process which is available. Now this strategy will actually produce the largest leftover hole, right? Unlike the best fit which produce the smallest leftover hole, the worst fit will give us the largest leftover hole, and therefore the worst fit strategy is more useful than the smaller leftover hole from the best fit approach. So for memory allocation, we say that the worst fit approach is most appropriate than the best fit and the first fit approach, right? Now, we understand that processes are continuously being assigned and we are using the different strategies. We are using the first fit or best fit strategies for memory allocation. But when these strategies are used for, memory allocation, there is another very important and very, crucial problem which comes up, that is known as fragmentation. Now, as the name itself suggests, the word fragment means part. And fragmentation means to divide something into smaller and smaller parts. So here also, when we are assigning the memory, whether we are assigning it using first fit or we are assigning it using best fit, because we said that in worst fit, the largest chunk is left. But here in these cases, there will be a problem of fragmentation. So what happens that when processes are loaded and they are removed from the memory, the free memory space is broken down into little pieces, right? Now we are talking about two types of fragmentation. One is called the external fragmentation and the other will be called as the internal fragmentation. So first we look at what is external fragmentation. So what is happening, that processes are loaded and they are removed from the memory, and whatever memory space is free, that space is actually not contiguous but it is broken, right? So the situation will be, or the scenario will be, that there is enough total memory space to satisfy a request, but the available spaces, they are not contiguous. That is, the storage has become fragmented into large number of small holes. So in totality, if we look at the available memory, it will be much larger. But if you want to actually store a process, you want to actually allocate, there will be no space which will be available. Why? Because all that storage is actually divided, or all that storage is actually broken down into smaller parts, into small holes. So this fragmentation problem can be very, very serious. It can be a very, very severe problem, right? Now we considered, we looked at the algorithm of the worst case, right? So in worst case, we said that we will have a block of free, or what we say wasted memory between every two processes. Now if these small pieces of memory, they were in one big free block instead, then we would have been able to run several more processes. But the thing is that the pieces are all divided, they are not remaining at one single place. So whether we are using the first fit or the best fit strategy, which can affect the amount of fragmentation, both these strategies will amount for fragmentation. Besides this, another factor is also there, that is which end of a free block are we allocating to. So whichever algorithm you use, whether you use the first fit or you use the best fit, right, external fragmentation will remain a problem, right? And depending upon the total amount of memory storage and the average process size, external fragmentation can become a minor issue, or it can even become a major problem, right? So, but this is a very important and very serious concern when we are talking about the memory allocation, that is how external fragmentation is taking place. So actually, there is a rule which is known as the 50% rule, because statistical analysis of the first fit algorithm and the other algorithms have also revealed that even with optimization, if you have n allocated blocks, then half of the n blocks will be lost due to fragmentation. So actually 1/3 of the memory is becoming unusable. Why? Because you have n blocks which are allocated and half of that n, 0.5 of that n are not available for being allocated because those are fragmented into small parts. So this rule is referred to as 50% rule, which implies that 1/3 of the memory is becoming unusable. Now memory fragmentation, we've discussed what is external memory fragmentation. There is another type of fragmentation which is known as internal fragmentation. Right? Now what is internal fragmentation? Now at the beginning of the lecture we talked about something called multi-partition, right? Multi-partition allocation means that there are multiple partitions which you have created, right? Now for example, we have created multiple partitions, okay, and we have a whole of say 18,464 bytes. So this much space is available, right? Now the process which comes, the next process which is requesting requires 18,462 bytes. So it will occupy the 18,462 bytes, but the 2 bytes will remain as a whole. Just 2 bytes will remain. Now this overhead of keeping the track of this 2 bytes will be very, very large, right? So in order to keep a track of these 2 bytes, it's better than the not having a record of this, because the whole is really small, it's only a 2 bytes whole, right? So what is there? The general approach is to break the physical memory into fixed size blocks and allocate memory in units based on block size. Right. So with this approach what happens, that we have already created fixed size blocks, right, and we are allocating memory to a process, right, which may be needing little lesser memory, right, than the size of the block. So now what will happen, that there will be small fragments or small holes which will be left within the partition, within the single block, right. So basically the difference between internal fragmentation and external fragmentation is that in internal fragmentation the unused memory is actually belonging to a partition, whereas in external fragmentation the unused memory is belonging to the entire system. So here within each partition we will have these small holes which are there. So this is internal fragmentation. So basically whatever it is, whether it is due to internal or it is due to external, this problem of fragmentation, it needs to be addressed. So we will be looking at how we can overcome this challenge of fragmentation, what are the strategies, in the continuing lecture, in the next lecture. Till then please keep watching CEC. Thank you.